So welcome to Physics 4480, Quantum Mechanics for Many Particle Systems. This is the official website of the university, and you will find, if you go in here, you will find the more details for the fall semester, and you will find things like a teaching schedule, and you will find teaching material. So I'm the guy with this funny name here. And then we have another guy with a much nicer name, Eyvind is here. The aim, or rather the setup for these lectures is that this week we are only going to have lectures. And you've probably seen that we have a slot of 4 hours for Fridays. We're actually not going to have lectures for 4 hours. I mean, you're going to go crazy, I'm going to go crazy if you just were to listen to me for 4 hours. And so we're going to split this into exercises and hands-on discussion of topics we have been dealing with during the lectures. And then from 10 or the second half of the Fridays, we're going to have more lecture-like. But in the beginning, on Fridays, from 8 to 10 or 8:15 to 10, we're going to have more exercise sessions and more active learning style of teaching. Since we have started today, there is not much which we're going to do tomorrow. So tomorrow we meet at 10:15. So there's no exercises tomorrow morning, if that is okay with everybody. And I will see if we can find a better classroom than this one, because this is not an optimal setting here. And we actually now we are 5, 6, I think we are supposed to be 10 or 11, which means it's going to be pretty crowded here. I'm going to switch a little bit between slides, but mainly on the whiteboard. And the whiteboard is basically to slow down the pace and actually give you the mathematical formalism which is needed. If you scroll down, you will find the GitHub address where we have all the teaching material. So we normally recommend you to actually just download what you have here. I'm going to update this material on a weekly basis. I'm going also to merge many of the notes into a textbook as a Jupyter book. So that's going to pop up after the weekend. You will find the weekly teaching material along this link here. So you would, actually, this is a link which didn't update properly. Yeah, this actually, I don't know why it didn't update properly, but I'm going to click on some of these links here, and then you can take a look at, actually, if you do a GitHub, a Git pull of the material. So let me just go back here. So in the folder here, what you will find is a set of additional folders. If you go to this doc folder, you will find in this pub folder, you will find basically the weekly material. So in second quantization is the one which I'm actually going to look at pretty soon. I will tend to switch sometimes between Jupyter notebooks and slides, but mainly I will actually use the whiteboard, which functions as my blackboard. If we go back again, you will find the README file here, where we have the basic information, where you find my office and Eyvind's office. We have 2 projects here, and they count each 30% of the final grade. And we also have a final oral examination. And the typical thing which we do in the oral examination is that based on what we've gone through during the semester, you can actually make a presentation based on that, and then choose among topics and present them as a kind of final, not exactly paper, but as a final presentation. We are going to cover several methods, but I wanted also to link to you the kind of textbooks. So you will typically receive a weekly mail where we have links to, there will be reading recommendations for different chapters in these books. So one book which is pretty okay and contains also a nice mathematical review in the beginning, in chapter 1. So I will essentially look at chapter 1 and chapter 2 of Sabo Östlund. if you go to this folder here, you will actually find the PDF files. Many of these books are actually out of print. So like Nagel and Hollande is a little bit more difficult to get hold of. So you will find PDF files of these textbooks. If you click into this link here, you will find Nagel and Hollande, which is a very good textbook on many-body physics. You have Sabo and Östlund, both the solutions to exercises and the textbook. So this is a book which has been used widely in quantum chemistry and also in atomic and molecular physics. Then we have another textbook, which is after Shavit and Bartlett, which covers methods like copper cluster theory. So the textbooks which you see here, they are essentially the textbooks which I will follow. So you will have my lecture notes, my Jupyter book, the handwritten notes, and then every week you will get additional reading recommendations. So in case you want to deepen your knowledge about things, you can dive into these textbooks. So this is a kind of, how to say, procedure during the semester. So the lectures often in a way serve as a kind of giving you the overarching view of why we do this, what is the basic machinery which we need to go through. And then if you want to dive a little bit deeper, many of these textbooks are actually well written, very pedagogical, and contain additional material. So you should have access to the textbooks. Unfortunately, I think Nagel and Hollande can be reached now. You can actually buy it, but the like this textbook by Reims is out of print. Sabo and Östlund is a textbook which is actually you can buy on I think if you, yeah. So this is and this is it's not a very expensive book either. Okay, any questions? Feel free to interrupt me here. And if
They're recording the lectures.
Yeah.
Where can we find the recordings?
So what I'm going to do then, if you go into the weekly program here, so I will actually put it into the weekly slides. But then I'm also going to set, after the weekend, I'm going to set up a Jupyter notebook, which will contain the detailed, no, not a Jupyter notebook, a Jupyter book, which will contain the detailed schedule. And at the schedule there, you will find a link to the recording. So you can also see here that there's a Zoom session going on. So I record via Zoom. So which means that if you are hindered from coming here, you can always attend via Zoom.
Does the Zoom link come via email or something?
Yeah, so that's also something which I will send to you guys. So you will get all this information when I'm sending a weekly email every weekend with the plans for the next week and reading us recommendations and so on. So you should be able then to actually, have all the information which is needed. So the videos, I mean, they will be uploaded, and I normally process them via YouTube because YouTube has actually improved its machine learning software. So it actually does a pretty good job in making subtitles. It's actually, you don't need to touch the file almost with the subtitles. It's pretty good. But that normally takes some, to digest 2 hours of lectures, I mean, it normally takes 10 to 12 hours. So it keeps going and now on and on and on. Okay, so the topics we will cover. So we'll have 4 lectures per week, roughly. You will get the weekly mail with all this kind of information to all participants. And this course is also a clone course. It has a PhD variant. And for the PhD variant, there's only pass, not passed as a grade. Whereas for the Master of Science variant, I mean, it's a standard grading, the letter grades. The topics which we will actually start today with some basic definitions. So we need to remind ourselves about some quantities which we've seen before in quantum mechanics courses. There's going to be some reminders about linear algebra, tensor product, the representations, and so on. So these are some of the basic mathematics tools which we are going to use again and again. So if unitary transformation is something you may have forgotten about. I mean, quantum mechanics is just about unitary transformations in one way or the other, period. That's the basic one of the basic mathematical operations. So that means that matrix relations, some linear algebra, tensor products, and so on are quantities which we need to dive into. So the first 1 or 2 weeks, we're actually going to look at that, and also representation of states, the kind of notation which we'll be using. We are going to look into ways to represent fermionic systems and systems of bosons. And when we've done that, we are going to switch over to what's called second quantization. This is also called the number representation. Actually, it's a kind of misnomer. There's no kind of second quantization or first quantization, but that's a kind of labeling which has been used for many, many years. I normally prefer number representation, and you will see why. And here we have several technicalities like the commutation rules, definition of creation and annihilation operators. There's something called Wick's theorem, which is a very powerful theorem, which allows us to efficiently calculate expectation values and transition probabilities. And there are many, many other small technicalities. And then we are moving into, for those of you who are familiar with quantum chemistry, FCI stands for full configuration interaction theory, which means that with a given basis, if you can set up your Hamiltonian matrix and you can diagonalize it, you basically solve the problem. However, you know that to diagonalize matrices means that you have to be able to deal with a certain dimensionality. And in quantum mechanics, as you will quickly see, dimensionalities are infinite. So in principle, we need to make truncations, we need to reduce the dimensionality of the problem. So many-body physics, the overarching way of looking at many-body physics is, or everything we do in solving physics equations is to find the right degrees of freedom. And when you've found the right degrees of freedom, to find the algorithm which you can use to solve the quantum, let's say the physics problem with the quantum mechanical problem. So finding the right degrees of freedom means the same as reducing the dimensionality of the problem. So if you think of a system like an atomic nucleus, ideally you would like to describe an atomic nucleus in terms of quarks and gluons, which represent the fundamental particles via this strong force. However, that leads to a dimensionality and a problem which is almost impossible to tackle beyond some few quark interacting quarks. So that means that you end up with proton and neutrons as effective particles and effective degrees of freedom. So physics, all of physics which we do, deals with finding the right effective degrees of freedom. And the mathematical formalism which you use is a formalism which allows you to link in a more fundamental way the effective degrees of freedom with a fundamental theory. Like for nuclear physics, it would be the theory of the strong force, but you're not dealing with a strong force because you have way too many degrees of freedom and you cannot solve it properly numerically or analytically. Most of the cases have very few systems which have analytical solutions. That does not mean that you cannot solve it, so you can solve it numerically. So these different many-body methods which you see here, they also reflect different mathematical algorithms. So the section which you see here, second quantization, is a way for us to represent in an efficient and compact way and have efficient calculation rules for setting up some of the basic ingredients for many-body methods. So this, you can see this as a kind of tool to compactify your formalism and make the calculations of expected values, transition probabilities, and so on in a very efficient way. Then FCI is essentially you translating Schrödinger's equation as a continuous problem into a diagonalization problem. Mean field theories is actually you reducing a complicated many-particle problem into a problem of coupled one-dimensional or one-particle equations, effective equations where each particle sees a field which is set up by all the other particles. But effectively what you're doing is to take a complicated many particle problem and you're reducing that one into a set of coupled single particle problems. And these are solved by iterations, iterative techniques. So it's a set of nonlinear equations. So that's the mathematical recipe. When you do many-body perturbation theory, which is a very popular method, mathematically that is a Taylor expansion around an energy. So you can think of all these many-body methods as ways to solve a complicated quantum mechanical problem with different mathematical algorithms. If you do couple cluster theory, that's a way to rewrite this full diagonalization problem in terms of nonlinear equations, and they are solved iteratively. So if you're familiar with nonlinear equations, you know that these are normally solved in an iterative way. If you go to Green's functions, which we will not cover, essentially this is you taking your Hamiltonian problem and rewriting that as a matrix inversion problem. So as long as you can deal with matrices you can invert, then Green's function theory is actually a method, mathematical method, which is very popular. It also allows you easily to bring in time. This similarity renormalization group methods, they're actually based on you rewriting Schrödinger's equations as a set of coupled ordinary differential equations, essentially. Monte Carlo methods is actually a stochastic way of solving the same equation. And that is taught in Physics 4411. So we will not cover Monte Carlo methods here, but you will find them in the Jupyter book. And then in this course, we plan also to say something about quantum computing. And we are going to look at one algorithm, which is called the variational quantum Eigensolver, which is used to actually reformulate quantum mechanical many-particle problems on a quantum computer. So different operations which you will do on states will be represented by unitary matrices. So quantum computing actually exploits the fact that the quantum mechanics is based on unitary transformations. And then we will also apply this to different systems. So we will have some schematic models. The electron gas is a widely popular model in solid state physics. And this is one of the cases where you can actually solve the mean field equations analytically. So this, if you do a mean field theory, the electron gas can actually be solved analytically. So you have an analytic solution for the energy of the system, but also for the single particle wave functions and single particle energies. So this is a rough outline of what we will cover. These methods are widely used in all of condensed matter physics, when you're dealing with systems in condensed matter physics, if you're doing quantum engineering, in order to construct quantum gates, if you're studying properties of materials, if you're doing nuclear physics, these many-body methods are kind of standard methods. If you're doing quantum chemistry, atomic physics, molecular physics, these are actually the methods which many people deal with. So this course also serves as an entry point for those of you who plan a master thesis in, let's say, quantum chemistry, if you're doing many-body nuclear physics or condensed matter physics. So you will recognize many of these methods here. Any questions so far? Things which are unclear? So the topic which I actually wanted to dive a little bit more into now are some of these definitions which we will need in order to get started with many-body physics. And I'm going to switch over to the whiteboard here and just try to use that one for most of the remaining part of the lectures. But before we move on, it would actually be interesting to know. I know some of you, but I don't know all of you. So it could actually be interesting to hear more about what is your background, what is your interest in this course, and what do you expect from this course. I can just start introducing myself. I've been doing many-body physics now I did my PhD on it, I did my master's degree on it, and I did my undergraduate work in Trondheim on many-body physics. So this actually took my first many-body course back in '85. That says a little bit about my age as well. And then I've been doing many-body physics in different ways. And lately, I'm very much interested in many-body physics and machine learning and many-body physics and quantum computing. So this course has some elements on quantum computing. It does not contain elements about solving Schrödinger's equation or many-body problems with machine learning. If you're interested in that, we have courses in the spring which actually deal with that. Maybe Øyvind, you'd like to say something about yourself?
My name is Øyvind. I'm a PhD student with mathematics and I also my master thesis was mainly on a couple of Oscar methods. I forgot here when he listed all these different methods, and specifically solving it for time-dependent problems. So you will, I believe, only look at the time-independent. Yes.
It solves much of the problems, but if you also want to phenomena, then you also need to move to the time-dependent domain. But this is the sort of starting point for this. So I have a PhD, so with master thesis and also my PhD. I guess this is my 5th year, I think, on the many-body.
My name is Sebastian. I'm doing computational science, and I took this course because I think it's interesting and I want to go at quantum computing, but it's as is later in the course, but it's.
My name is Coulomb. I am also a first-year student of computational science physics. I did this course because I thought it was interesting, and I think I wanted to do a master's in something related to regions. I'm Johannes. I'm a first year at computational science physics as well, and I took this course because I think it's interesting to look at many-body systems.
I'm Daniel, also first year master's at Computational Science Physics. I went to take this course because I think the idea of quantum mechanics for anybody, it seems interesting. I'm not sure. I want to find out. And I also want to, in the future, if it works, if I like it, mix a little bit of machine learning with it and see what happens. So that's it.
My name is Håkon also. I'm a PhD student. My supervisor is Simon Cole.
Right.
Yeah, I work there. Yeah, I know. I know. Yeah. So I will be working on a couple of cluster methods. I'm part of a new research project, which aims to combine some theory on quantum information with these methods to essentially solve Schrödinger's equation. So I'm cooperating with people in the math department, joint project, but at this point I really do not understand anything, and I don't know what I'm supposed to be doing. So I just came here to have a look at what's going on. And Simon said maybe I should be here also.
Yeah, I mean, they had this course for previous fact.
Yeah, it's even what's going on. Yeah. So that's what I'm doing.
Cool.
Yeah, I'm Jörn. I'm in the 2nd year of my master's in computational science chemistry. I took this course because I'm interested in systems, and as I am a chemist, I probably should know a little bit about it. So I hope I will comment.
I am Gianmarco. I'm from Italy. I'm from the University of Trento. And I'm in the 1st year of my master, and it is about theoretical and computational physics, sort of similar to the computational science physics here. And I was interested in this
in this kind of topics, even if I don't know still what I will be doing in my master in the future. But I am here to see.
My name is Skalvik. Technically finished with my master's. I'm next to
Cool. So I'm going to put back these because give us some more better quality for the recording. So as I said, I mean the GitHub website will be updated on a continuous basis. So just feel free to clone it and use it as your own teaching material. I'm going to, I haven't punched in everything I'm going to say today because I've changed a little bit things. But you will get the written material as soon as possible. The notebooks which we are going to produce here now, this is something which I will mail you right after the lectures today. So you will have access to my notes in addition. So the handwritten notes, but also the notes in the Jupyter book. And the ideal is that you will get a message roughly before the week begins so that you can see what are the plans for the week to come and what kind of exercises we will deal with. I put up a kind of tentative deadlines for the first project, and I put that to roughly the middle of October. And then, so these are projects which are not like the projects many of you have seen in computational physics or other courses. It's actually more answering questions. So just like a set of exercises. And they're going to contain some numerical elements as well. What we can also do is that we can tailor a path to those of you. So suppose now there are people who are more interested in copper cluster theory. We can always make different variants of the second project. So these are actually not projects, but they're like midterms. And the second midterm, we were thinking of having roughly a deadline in the middle of November. And then we can decide among ourselves when we want to have the oral examination. So this depends on your schedules. And typically in this kind of courses, when people like to have the final examination more closer to when the winter breaks begin. So that means roughly in the second half, or let's say 15th of December, something like that. But we can always adapt to that, to your schedules. So we are a little bit flexible with that. It depends also on the external examiner when we can get that person. So, but send me an email about your preferences for the final oral examination. And then we will try to set up a schedule for the final oral exam, if that's okay. Because the person upon which everything hinges is actually the external examiner, because that's the person who has to come here. Okay, so many of the things I'm going to talk about, you will find that in the link here, but I prefer normally in this course to use a whiteboard or blackboard just to slow down the pace. So let's switch to the whiteboard. By the way, if you guys are interested in quantum computing, one of my PhD students in the USA defends his thesis tomorrow at 9 o'clock in the evening. So if you're interested, I could send you the Zoom link and the thesis as well. Okay, so what we will need now is actually some basic definitions. So let's just write down here physics 448. So this is now August. And we need some basic definitions. And I'm going to take this one away so it doesn't disturb us. So is it okay? I mean, the size of the letters and everything? Okay. So we are going to have a specific notation, and we're going to use this Dirac bracket notation. in order to represent states. So that means that if we have a vector, and this is a vector with n elements, so this is a typical way we are going to represent quantum mechanical states. So the states we are going to represent can be states representing just one particle, but it could also be a many particle state. So whether it's a one particle or many particle state is something which will be obvious from the context. So this means that we will have a vector like this, x. So this is the kind of compact notation which we will use, and that's going to be represented by a vector with elements up to xn minus 1. So I'm going to use this kind of Python C++ like notation where we start with the 0th element. I hope you don't mind. And this is a vector where the different x's, they will be elements in, or we can just write x itself as an element of, can be real, but in general it's a complex quantity. Then we are going to define the bra state, which is simply given by the Hermitian conjugate, or sometimes we just call it the adjoint. So there's a kind of mixing of words. So Hermitian conjugate or adjoint. I'm just gonna use them in a kind of perhaps not always consistent way, but this would be the Hermitian conjugate. And we are also going to write this quantity as, obviously, x, and this is the sign for the Hermitian conjugation. So these are kind of notations which we are going to use here. Now, we are going to assume in many cases that we have a so-called orthogonal and normalized basis, and this is normally written as an orthonormal basis. And that means that the norm of this quantity x of x is equal to 1. If I have another vector where I take y times x, this is the same as multiplying the vector x, y with x, and this is something which we would write out as an I from 0 to n minus 1, and then we would have a yi complex conjugate multiplied with xi. I hope I am not offending you with some of these basic definitions. There's another quantity which we are going to use repeatedly, and that is the outer product. So if we take the outer product of two vectors like this x and x, so this is defined like this. This is a matrix. And the reason why we're going to put a lot of emphasis on this is that this quantity is going to pop up again and again and again, either in terms of so-called projection operators, where we can split the effective space into, well, Hilbert space into an effective space and an excluded space. So this quantity here is something you will see over and over again. So this would typically now be x0 times x0. You would have x0 times x1, and this goes up to x0, xn minus 1. And then down here we would have xn minus 1 times x0, and then we would have xn minus 1 times xn minus 1. And it's pretty easy to see also what the outer product is going to be for x times a vector y. Another quantity which we are going to use repeatedly, yeah?
Isn't it the complex conjugate? Isn't it the complex conjugate?
Oh, sorry. I forgot that. Sorry. You're right. Thanks. I forgot to put the asterisks here. Thanks. Now, another quantity which we are going to use again and again are so-called tensor products. And the compact notation, which you will see again and again in this course, is a notation which actually implies that a tensor product has actually been taken. So let me give you some basic definitions here. So if you have a vector x and you take the tensor product with a vector y, this is often written in a compact notation like xy. So this can be a little bit misguiding, and it will depend very much on the context you are in order to see what this actually means. So let's take an example here. Let's now suppose that this vector x is actually equal to a standard spinor with two elements. So this could be 1, 0. Often you would see this one labeled as 0, like that. So later, when we're going to introduce some basic elements of quantum computing, these states are going to be recognized as the qubits. So you will have a qubit 0 and a qubit 1 if you have a two-state system. So this is an example of a two-state system. Then we could think of the vector y to be given by 0 and 1. And you will often see this labeled as 1 here. And that could be qubit, 2 qubits. There you have a two-state, which then form a computational basis. So I'm also going to introduce a concept of the computational basis here. This computational basis need not be the eigenbasis of the full Schrödinger equation, but it could be the eigenbasis of a reduced part of the full Hamiltonian problem. And it's very common, you are going to see this again and again, that we are often trying to find a computational basis which we use as an ansatz for solving a many-body problem. So think of atomic physics. You're all familiar with the hydrogen atom, right? And you know that you can solve the hydrogen atom analytically. And that gives what is normally called in the literature for the hydrogen eigenfunctions, or just the hydrogen basis. And these are given by Laguerre polynomial times an exponential function. So there you can solve the hydrogen problem is something you can solve analytically. Now, when you want to make a model for the helium atom, you can actually use the hydrogen basis as a computational basis. But if you make a many-body function of that, that is not an eigenbasis of the helium atom, but it can serve as a part of the solution. So you will see that we can actually extract from the whole Hamiltonian a part of the Hamiltonian which has this ansatz as an eigenbasis, and that defines a computational basis. So I'm going to come back to this again and again and again. So you will hear me talking about the computational basis because that's the basis we often use as an ansatz to build a many-particle system. So you can think of this as a kind of computational basis. You see easily here that if you want to calculate y with x, this is obviously equal to 0. That should be pretty obvious. If you take x and x, take the inner product here, this is equal to 1. And the same with y times y, this is equal to 1. Now what we could do now is to take the tensor product of x with itself. So x is now a vector of length 2. When I take the tensor product, this actually means that I get a new tensor where I now have 1, which is multiplied with 1, 0. So this is a definition of the tensor product. And then I have 0, which is multiplied with 1, 0. And this becomes simply 1, 0, 0, 0. You would see this often written now in a compact way as XX. You can now do the same thing with X and Y. You can do the same thing with Y and Y. So what you would get then, when you do all these operations, is that you would get a new set of states, and often this one, since we have labeled this x as 0, it's not uncommon to see this as 0, 0. So this could now actually represent two physical systems. So you could think of the first one as one specific system and the other one as another specific system. Alternatively, if you now think of a wave function for a single particle, so if we now take a single particle wave function and we think of the hydrogen atom, for instance, or state function, you have often seen this written as a spatial part, where you have some specific quantum numbers alpha, and then you have the spatial coordinates. And this is actually the tensor product with a spin part. So you will now have a spin part where you know that S, the spin, is a half, and then you only focus on the spin projection. Normally, what you would see is that this is often written in a very compact way as a function which you would write like and normally you skip R. So we're actually going to often leave out the spatial degrees of freedom, and we are going to look at quantum numbers alpha, and then you will see something like an MS here. So that would be a kind of compact notation for this type of wave function, where we now have taken out, so I shouldn't write an equality sign because I've actually dropped R. So in principle, I should also keep R here. But then you would find this in a second quantization notation, where we skip the spatial degrees of freedom, but where we actually represent this in terms of quantum numbers alpha and the quantum numbers for spin. So these are compact notations. I'm bringing them up because actually when you're setting up a single particle wave function, this is normally the tensor product of functions in different spaces. So you would have spin space, you have the spatial degrees of freedom, and the way you can think of these alphas now are slots with different types of quantum numbers. So since this is a typical hydrogen-like wave function, this could, if you think of the hydrogen, this could be represented by n, the number of nodes the wave function has. You could have, since you are in 3 dimensions, then you have 3 quantum numbers. Every dimension brings in a quantum number. So NL, and you would have ML here. So this would be the quantum numbers if you're dealing with a hydrogen atom. So I'm just specializing here to the hydrogen atom. And then we postulate that these particles have spin a half. So there is a spin part that lives in another space. So the total wave function is actually a tensor product of the spatial part with the spin part. The kind of compact notation which we often end up with is something like what you see here. So this is a typical compact notation which we are going to use. Sometimes when we actually deal with states, if you think of a state like this one, you will even see that this one becomes reduced then to a new computational basis, and where this one is actually given by just 0, just to add to the confusion. So tensor products play a very, very important role in what we are going to do here, but it's normally hidden in the sense that we end up using a more compact notation like this, but you have to think of this as a tensor product of different spaces. So this is for single particle. And then when we are making a many particle state, that would be the tensor product of all the single particle Hilbert spaces. So these states which you see here, they would then define the single particle Hilbert space. And from the context, you will see whether this is a many-body state or a single particle state. Now, we have actually gone a little bit over time here. So I was actually thinking of taking a small break. So I'm just going to put the recording on pause, if that's okay. And then we stretch legs a little bit, and then we continue with some of these basic definitions next lecture as well. And when we also do some of these things tomorrow. Okay, after this small break, we're going to continue a little bit with these kind of definitions, but then we need to go into the kind of systems we are going to look at. So we're going to look at some examples of basis sets, but also on the type of Hamiltonians which we are going to meet. And the way we are going to set up the problems is that we will try to find parts of the Hamiltonian problem, which enters the Schrödinger equation, which can be solved analytically. And this basis, which we can obtain from the analytical solution of parts of the problem, is going to normally define the computational basis. But let's look at some of these examples which we had here. So we could now, since we have introduced this notation with 0 and 1, so you could think of this as a system with two states. The original system, your computational basis. You can now rewrite this system, which we wrote as X cross product with the tensor product with X. We can rewrite this as a 0, since we defined X in terms of this vector, which is a spinor actually, it has only two elements. And then we ended up with the same notation which we had before the break. And this is a vector which is defined like this, 1, 0, 0, 0. And then we could have a new state where we take the cross product with a 1 here. And that would clearly give us a new state, which we are going to have a 0. And then we would have 1, 0, 0. And this is going to be the state which we call 0, 1. And similarly, we can do 1 with 0, and that's going to give us a new state, 0, 0, 1, 0. And this is something we could label as 1, 0. And then finally, we would have 1 and 1. And this is something which becomes 0, 0, 0, 1. And this would be 1, 1. Now, what you see rather immediately is that if you look at the norms of these vectors, or the inner product, if I take 1, 1 with 0, 0, and you calculate that one, you see that this basis is also orthonormal. And then the only one which would be equal is like the 0, 0, that would give us 1, and similarly with 1, 1 would give us 1, and if we take 0, 1, 0, 1, that would also give us 1, etc. So what we have constructed now is actually a system which is a tensor product of two computational bases. And later, when we are going to look at concrete specific examples, we are going to link this with specific physical systems. But now we're just defining the tensor products. I guess you're pretty familiar with the tensor product of matrices, so I don't need to repeat that. But the thing which I wanted to bring up is some of these identities which we can rewrite in terms of specific operators. So if I now look at this inner product of 0, 0, no, not the inner product, but the outer product, sorry for that. Then this becomes simply a matrix, a 2 by 2 matrix, which is given by 1, 1 along the first diagonal and 0 for the rest. Then, if I take the next vector, 1, this becomes simply 0, 0, 0, and 1. Now, my identity is given by the sum. So this is a definition now, where I can sum over all the computational basis sets up to n minus 1 of I. And you see now, if I take this specific example, where my basis set consists only of 0 and 1. So if I now look at the specific case where my I equals 0, that corresponds to the state 0. And then I stop at I equal to 1. and that corresponds to state 1. For this specific case, then you see now that when I add these two matrices, I have 1, 0, 0, plus 0, 0, 1, and you see that this is the identity matrix, like that. Now, why do I bring up this? Now, the reason why I bring this up is that it's normal to split this relation in terms of at least two pieces. So what I could define now is to define an operator, and I'm going to put a hat on top of that one, which now is given by this matrix 1, 0, 0. And then I could define a new operator, which is now defined in terms of this matrix 0, 0, 1. So what this one is equal to is actually this first state, 0, 0, and this one is equal to 1, 1. Now, the reason why I'm doing this is that I'm going later to reduce my Hilbert space to a smaller space, which then consists or defines an effective Hilbert space. And then I'm going to look at the rest as an excluded space. And the hope then is that I can rewrite Schrödinger's equation in terms of blocks, one for an effective Hilbert space, which is a reduced problem, and then I have the excluded space. So let's take a look at these things before we move on. So I want to stay a little bit more general. Now, if you look at these operators which I have defined, you can easily see now that if I take p squared, this is equal to p. So if you just multiply the matrix P with itself, you will find out that this is equal to P. So this is an example of a so-called idempotent operator. And then you will also see now that Q squared is equal to Q. So that has the same property. And it's also easy to see when you multiply these matrices with each other, P times Q, this is equal to 0. So these spaces are orthogonal spaces to each other. So we are going to call these projection operators, and you're going to see why they are projection operators. And they're going to play an important role in creating an effective Hilbert space, which hopefully is a space where we can solve the many-body problem, either by diagonalization, or we can use copper cluster theory, or any of the many-body methods which we mentioned. So everything we are going to do in this course, and everything we do in physics in general, and science in general, is to try to find ways to reduce the dimensionality of the problem. So if you're doing quantum computing, that's also a way to circumvent the fact that the dimensionality of the problem explodes. So in principle, this summation which I put up here, this summation is actually an infinite summation. So we need to make truncations. So the typical thing now which we do is, so we have defined I equal to this operator P plus Q. So we can now define this in terms of a set of states where we sum up to a dimensionality D, where we have Y of I. And this is going to define this operator P. And then we have the next part, which is an I equal D plus 1, and in principle to infinity. Now, why is this a projection operator? You can now see that because if we have a computational basis, so if our computational basis, which is an orthogonal basis, is given by 0 and 1, so we have a two-state system, so it's fully possible to define a problem with only two states. Then we know that we can make linear combinations, so this is an orthonormal basis. So we can define a new state, phi, which is now a linear combination of these two states. So we are now assuming that this computational basis is a solution of parts of the full Schrödinger equation. So that means that 0 and 1 are not necessarily the eigenbasis of the full problem. However, we know that we can expand the exact solution in terms of an orthonormal basis. So in principle, what we know is that this phi here, that can be expanded. So if we have a basis I equals 0, and this basis is actually infinitely dimensional, this is given by the overlap coefficients between this basis phi and then the states I. So I is a handy computational basis. It's an orthonormal basis, and you know that when you have an orthonormal basis, you can actually expand another state in terms of that basis. So this is one of the mathematical ingredients which is going to be very, very important in this course. So what we are doing now, so keep this in mind, we have chosen a computational basis, and we are going to use that one as an ansatz to define the exact solution. So we are expanding the exact solution in terms of a basis which we know how to use. We know the eigenfunctions. Often these are analytical functions. If you're dealing with hydrogen-like basis functions, these would typically be Laguerre polynomials, and we know their properties. And what we are doing now, we are expanding a more complex system in terms of that basis. So this mathematical property of orthonormal basis is something which we are going to use again and again. So when you now go back to these operators, if you now look at this operator P acting on the state phi, what that one is doing is actually that will project out the component 0. So it's going to project out a specific component of the full wave function. So this is going to be given by this matrix, which we have 1, 0, 0, and this is acting on 1, 0 plus beta 0, 1. And when you do the mathematics here, what you see then is that this becomes simply alpha times 1, 0, which is again the same as alpha times 0. So what you see now is that this operator, when you have a linear expansion in terms of this computational basis, this actually projects out a specific part of the wave function in terms of a computational basis. So you will hear me repeating these things again and again, because this lays the foundation for the starting point in many-body physics. So we always start with some kind of ansatz for the wave function. And that ansatz is often set up in terms of a part of the Hamiltonian which can be solved analytically. And that part of the Hamiltonian is often motivated by the physics of the system. So if you now take the vector Q here, notice the operator Q and act on that one, it's easy to see that that projects out this part of this state which we have chosen as a linear combination of the computational basis. So these are some kind of technicalities. I'm going to introduce another quantity which we are going to see again and again, and which also plays an important technical role in many-body physics, and that's called the density matrix. So you may have heard of that one. And when you do quantum computing, the density matrix is a central topic. So the density matrix, if I now take this state, phi, which we defined, so I can define, so I'm just putting up the definitions, and we are not using them in specific physics applications yet. If you look at that one, the way this is going to look like when you run the calculations is that you're going to have the state alpha and beta, because if you look at, let me just go back a little bit, you can rewrite this in terms of alpha and beta. So it's a linear combination of your computational basis. So this one is given now in terms of alpha complex conjugate and beta complex conjugate. So this is now an outer product, remember that. So when we do the outer product, this becomes equal to alpha times alpha complex conjugate, and then I have alpha times beta complex conjugate, and then I have beta, and then alpha complex conjugate, and beta times beta alpha conjugate. Now, an important thing here, when you take the trace of this matrix, so if you notice that, if you look at that one, so you take the trace of the matrix A, this is actually given by the sum of the diagonal elements. And then what this becomes is actually this quantity plus this quantity, and that is equal to 1. So the trace is 1, and that's the sum of all the probabilities. So you can write this as the sum of all probabilities. Later, when we are going to touch upon quantum computing, if we get there, then the trace is going to play a fundamental role in order to study whether a system exhibits entanglement or not. So now I'm just giving you the definitions here. So the trace is a quantity which we're going to meet again and again. And it's a calculational quantity, which is also handy when we are dealing with equations like the Hartree-Fock equation to set up not the trace, but the density matrix. So this is a quantity which you will see again and again. You will also encounter these operators P and Q when we are setting up or rewriting our Schrödinger equation. Now, one of the things I wanted to say a little bit more now is about the way we are going to set up the Hamiltonian and the link with the computational basis. So let's go back to this with computational basis and look at some examples. So one typical basis is actually the harmonic oscillator. And this is a system or a kind of basis which is appropriate if you're looking at, let's say, bosons which are confined in traps. So boson condensation and boson condensation, the whole field of the condensation of dilute gases, which led to a chain of Nobel Prizes in physics, is something which is based on you being able to trap atoms which act like bosons in small areas. So what typically is done then is to set up electric fields, quadrupole fields, and they look like a harmonic oscillator because a quadrupole field goes like x squared plus y squared in 2 dimensions. And you can actually trap these atoms or ions in these kind of small traps, and they're called Paul traps or Penning traps. That was another Nobel Prize in Physics in 1989 for the whole trapping technique. And in that case, these traps, they do look like harmonic oscillators. But then the system will also consist of particles which interact with each other. So they can repel each other or they can attract each other. So there will be interactions as well. But if they're not interacting, this can be thought of as an idealized system of particles in harmonic oscillator traps. So just to remind you of that one, so this is a system which you will find in problems in solid state physics like quantum dots or artificial atoms. We have Bose-Einstein condensation. We have nuclear physics. It's pretty common to use a harmonic oscillator basis. If you're doing molecular physics, it's actually pretty common to use a harmonic oscillator basis. So if you now look at this in 1 dimension, what we know then is that the particles This is just one single particle that is trapped to move in a harmonic oscillator potential. And then we know that we have discrete energies. So we have nx equal to 0. We have nx equal to 1. And we have nx equal to 2. So these are the number of nodes which the wave function has. And then this goes actually to infinity. So we have an infinite basis. So this could be an example of a computational basis. Now, this is normally a solution to a problem where we have analytical solutions. So I'm also going to change a little bit the notation. So nx refers to the number of nodes. And you know that the energy here differs by a unit of h bar omega. So the energy, this epsilon nx, is now given by h bar omega, and it contains nx plus a factor of a half. So that's the harmonic oscillator energy. So this is a typical example of a computational basis, which is highly relevant if you're dealing with, let's say, quantum dots, or you want to study Bose-Einstein condensation or similar systems. Now, let's now introduce the Hamiltonian for this system. So we are dealing with one particle here. Yeah? What? Thanks. Okay, so the Hamiltonian in this case, I'm going to write this as an H0 with a hat to indicate that this is an operator. And this is going to contain the kinetic energy. So we will have a minus H divided by 2m. And in our case, this is just a one-dimensional problem. So this would just be d dx. And then we have the harmonic oscillator potential, which in this case will be 1/2. And then we have a parameter k, and then we have x squared. So this is the Hamiltonian operator. And here we have analytical solutions. So that means that when H0, so we define the computational basis. So we define a basis now, which now contains these quantum numbers nx, and it has an x dependence. So formally, this is normally seen as this definition here with nx. Now, I want to make this general now. So I'm going to transform this nx to just an index I, just to keep it more general, because then we can look at a general basis. We don't need to think of a harmonic oscillator. So that means that we have a basis where we have the states I, which go from 0, 1, 2, and in principle up to infinity. Now, you see immediately now one problem which we have to deal with. We cannot deal with infinities. So one of the things which we end up doing in many-body physics is to make a truncation here. So we will truncate at some value lambda. Yeah?
Just to warn you that your MacBook is,
Yep.
the battery is low. I don't know if you have seen it because you're looking at the iPad, so.
Okay, so yeah, you're right. I need to charge it. Thanks for saying that. But then I'm going to, okay, so let's now see here. That should function here. You have to buy all these peripherals with Macs.
Yeah.
And every time they come with a new one, you have to buy a new set of these. And every one costs something like 300, 400 Norwegian
At least
kroner.
now it's USB-C, right? Because in the past it was.
Yeah, when I have my iPad on it, it's actually discharging here. Oops. No. Right. There we are. Now it's charging. Thanks. That's always a problem when you have all these gadgets here. You always end up with a... So you see now that you have a truncation. This is actually the first truncation we make. In the computational basis. So that's an approximation which we actually end up doing. And in some cases, we cannot quantify the error we make by making such a truncation. So this is actually a serious problem in many body physics, that sometimes we cannot quantify properly the error we do by leaving out some states in the computational basis. So what is normally done then is that you would run a calculation where you just keep increasing this value of lambda till you reach some kind of convergence. So that's the first truncation in the computational basis, and this is normally done at the level of a single particle basis. So when we now are constructing a many particle basis, what we would typically do then is that we would distribute the particles in these states. So if you have bosons, then you can have an infinity of particles in the first state. But if you have fermions with the spin half, so if you're looking at the fermion case, what will happen then is that you could think of now filling up, so you could have a spin up. So the arrow up is a spin up, and a spin down case. So this could be an example of a two-particle state in the computational basis. This may not be an eigenstate of the full problem. So if I take the helium atom and I use a hydrogen basis, and I just place the two electrons in the first 1s orbital from the hydrogen basis, that is not the eigenstate of the helium atom, but is a good approximation to the helium atom. So I'm going to go a little bit back and forth in this just to have you with me on the way we reason in many body physics. So we have to live with this truncation because in principle the computational basis we choose is an infinite basis. So the case with these bits 0 and 1 which I put up, that's an example of a two-state system, but that's an idealized system. In most of the bases which we end up using, we have an infinity of states. Now, the thing we end up with here, when you look at this H0, so we have now a state phi, so we're going to replace that one with just a state, which I'm going to label with phi I of x. And we are going to have the Hamiltonian operator acting on this state. And this has an eigenstate with energy epsilon I, and this is multiplied with phi of ix. We are going to use a more compact notation, and we are going to take away the spatial degrees of freedom. So the way you're going to see that one is actually a notation where we just take this state I, and we rewrite that one in terms of epsilon I times I. So this is the kind of compact notation where we've taken out the spatial degrees of freedom. So when you're calculating this quantity here, you would typically evaluate this in terms of an integral. So if I multiply with phi of I complex conjugate and integrate over d of x, then I get the energy epsilon of I. So this is the kind of notation which we are going to use. So this is the we normally call this the one body operator because it acts on one particle at a time. Now, one thing which you would see now is the following. So the full Hamiltonian, and now we are talking about the many-body Hamiltonian, that is going to include the kinetic energies of the single particles. So I equal 1 up to the number of particles which we have. So uppercase N is going to represent the number of particles which we have in this course. So this is number of particles. And we are going to have a kinetic energy piece, which we are going to write like this. So this will have a delta I squared. We are now specifying this to be a three-dimensional object. and then we have 2 over m of I, if the particles are different. Then we may have an external potential. The harmonic oscillator is an external potential which confines the motion of the particle. So that means that we can just rewrite this as a sum of I up to n. And we are just going to label this as a V external. And this will depend on some x of I here as a vector, since we now are going beyond one dimension. So this is the one body part of the Hamiltonian. And we are going to label this as an H0. Now, the specific thing with this one body part is that when it acts on a many-body state, where we have used this single particle basis as an ansatz, this single particle basis turned into a many-body basis is going to be an eigenstate of this H0. So the next part, so this is normally a sum of one-body operators, but then we are going to have a two-body Hamiltonian. We can have more complicated ones, 3-body, 4-body, and so on. But we will mainly limit ourselves to two-body Hamiltonians. If you're dealing with nuclear physics, you may actually have to deal with 3-body forces, effective 3-body forces. You also have effective 3-body forces if you deal with ions and atoms, ions in lattices, and so on. So, but let's be very generic here. So this is a double sum over all the particles, and this contains now an interaction, and typically this interaction is a function of the relative distance between the particles. That's the standard. If you think of the standard Coulomb interaction, that is a function of the inverse relative distance between two particles. So we would typically rewrite this in terms of an xi vector minus xj vector, like this. And typically you will see this one replaced by something like xij, since this is an absolute value now. So it depends often on the relative distance. But if you wish to be a little bit more general, you could actually replace this one with an interaction. So let's just put this in a kind of parenthesis here. You could just rewrite this as an xi xj. Now this part of the Hamiltonian is normally called h of I for interaction. This zero could be thought of something with zero interactions. Now the thing now is that if I construct, so I can construct, and we are coming back to that tomorrow when we look at the construction of a many-body basis based on the computational basis. So construct a many-body ansatz, which I'm just going to call, so I'm going to use an uppercase letter, and I'm going to label this as a state I as well. It's just a summation index based on the single particle computational basis. So that means one thing we could do is, for instance, to say that this phi of I, as an example, this could be the product of all the single particle states which we have. So suppose now I have a sum over j equal, start with 0, and then I have up to d single particle states. So I have made a truncation in the single particle basis. And then this is just a product of this j, and then I would have now different single particle states, and they will actually, so you could think of particle j being in a quantum number j. So think of, if you spool back here and look at this specific example here, you could now think of having many particles, and in every J here there's a slot. So this would be slot 1, this is slot 2, this is slot 3, this would be slot 4, and so on. And in each of these slots, you have placed a particle. So what you've chosen here is a specific ordering. So you start with the lowest one, and then you simply multiply everything like that. Now, this has a problem, as you may see immediately. If these are fermions, would this be a realistic ansatz for the fermion problem? No, it doesn't obey antisymmetry. This state also breaks with the standard symmetry you would have for bosons. So a product state like this is not the correct ansatz. But let's leave that as a problem for tomorrow. And the thing which we are going to state now, without proving it, we are going to calculate that later. So tomorrow is actually the day when we are going to calculate and show that these things lead to the eigenstates of the unperturbed Hamiltonian. So what we are going to state now is that if I construct such a basis, so we are rather, instead of this one, we are going to say that this is proportional to the product. So not equal, but proportional to some kind of product. But the thing now is that this basis, if this single particle basis is an eigenbasis of the single particle H0, this is also an eigenbasis of the many-body H0. So that means that H0, no, sorry, not that one. So this is going to be an eigenbasis of this E of phi of I. So tomorrow we're going to show it, that this is actually an eigenbasis, but now I'm just stating it. So what we have done now is that we have H0 multiplied with the single particle basis like this, and this is given by an epsilon I times phi of I. If I now construct a many-body basis on this computational basis of orthonormal states, then this many-body state is also going to be an eigenbasis for the unperturbed or the non-interacting part of the Hamiltonian. So that means that the exact, so let's see how we do in time here, the exact wave function or state function where we take the full Hamiltonian, multiply with a psi, and now we can look at a specific state K. This is now given by the true energy of the system multiplied with this eigenstate K. This state psi of K is now something we can write out as a linear expansion of the computational many-body basis. So that means that I will now have a J equal to 0, and then I have a set of states, D, and this is now given by the overlap, Ck of J, and then I have my computational many-body basis. So this is the many-body basis, computational many-body basis. Now, this truncation D is not the same as a truncation which we put up in the single particle basis lambda. So here we put a truncation lambda in the single particle basis, but that's not the same truncation as the one we would have in the many-body basis, which I label as a D here. To see that, let's look at an example with fermions. So suppose now you have a single particle basis, which looks like this. So we have a given number of states, and suppose we end up with n single particle states, and we start with 1 here, 2, and so on. And these are states with a double degeneracy. So I can have, let's say, 2 fermions in every state here. Like this. I can build up. So suppose now I have 4 particles. So what I'm having now, if these are fermions, you have to keep in mind now that you can have only 1 fermion in 1 slot. So you would have slots here. So in total, you would have 2n single particle states. Okay, so the total number of ways you can distribute these 4 particles, total number of fermionic configurations you can make, fermionic states, we also call them configurations, that is going to be given by the binomial factor of 2n with the number of particles. So this is just plain statistics with replacement. So this would be the same as 2n factorial. And then I would have 2n minus n factorial. And then I would have n factorial. So this would be the total number of many-body states I can make. And now I'm not paying attention to symmetries or anything. So you can quickly see that this grows immediately. So if you have something like 80 single particle states and 40 particles, this is beyond what you can diagonalize with standard diagonalization methods. So that means you need to truncate your space. And this is where you have the second truncation. So the first truncation we made was in the single particle basis, which then translates into this number here. So that's one truncation we make. And then, based on that truncation, we have a limited set of configurations here, of many-body states. So what we can decide now is actually to make a truncation here as well, to not include all the states. So you can actually make, these are the 2 most standard truncations which you make. Alternatively, you can now define an effective Hilbert space and think of this as your full Hilbert space, but you have defined some kind of effective operator which lives in that space. So you've reduced the dimensionality. And then you could say that now I define a new Hilbert space which looks like this, where I'm going to run my calculations. So that's an additional truncation. So all the many-body methods which we are going to deal with, they address one or another way of these type of truncations. So what I wanted to have you with me is this way of thinking. So we start with a computational basis, and this computational basis is a handy basis because we have normally analytical functions. With those, we can construct a many-body basis, which is still a computational basis, which is an eigenbasis of parts of the problem. And then we know that since this is going to be an orthonormal basis, then I can always expand my exact solution in terms of this basis. You see the basic philosophies? This is what essentially many-body physics is, to find efficient ways of defining an effective Hilbert space, and then use one of the methods like full diagonalization. You can use many-body perturbation theory. You can use copper cluster theory to actually get an estimate of the ground state energy or other excited states. So I'm going to stop here.